Okay, in the previous video we spoke about integration as adding up infinitely small things, and we will see that also in this video, but this is a different type of, well, the concept of adding up infinitely small things is going to be there, but yeah, let's see what happens. Okay, so the integral of a positive function of a single variable is defined as the area under the curve if it's a positive function. More or less, this is what you're dealing with. If you want to see this, well, look at the previous video and try and break this area up into infinitely many small areas and estimate it and see what you get. Well, that's what the integral is. Okay. Now, what I want to focus on here actually is that you're adding up between A and B. So you're chopping the area up into loads of different pieces like this, and you're kind of estimating these things, say these little strips. So suppose we've got delta x is very, very small. Now there's lots of things that are confusing. If delta x is infinite, if the number of rectangles is infinite, delta x is 0. If delta x is 0, there's all these kind of paradoxes. Leave it to the pure mathematicians to figure it out, and they understand the theory very well. But imagine this is very, very small, is the width. And what you're doing is you're adding up this thing now. In fact, you can almost think of this as infinitely thin. And that's how the area is infinitely small. And you're adding it up. You're adding up all these areas. So there's one of them at A as such. And there's infinitely many the whole way over. There's these little strips. They're all infinitely thin. And you're adding them up from A to B. So I want you to have this concept of adding up from A to B. So there's a few things I could write down here. So the integral from A to B, you want to think about it as adding up from A to B. This thing is just, this interval can be written as AB. I could write it as adding up from A to B. Now these should probably be integral signs because they're infinite sums. Or you can think about, this is the big one, adding up over the interval from A to B, integrating over the interval from A to B. Now what we're going to see is that it's not just intervals that you can sum over, you can also sum over areas and volumes. So think about an area. Suppose you want to find the second moment of area of a region. What you need to do is add up the second moment of area of all the little parts of that region. They're two-dimensional and you have to sum up over an area. Or suppose you wanted to find the mass of a volume. What you do is you chop it up into loads of little pieces and you add up the volumes of all the little pieces. You need to add up over the volume. So these are what are called double integrals and triple integrals. Okay. If you have a function of two variables, its graph forms a surface, and here we've got a positive function. Now, this is something like z is equal to a function of x and y. Now, I'm only going to, I can talk about, okay, you've got areas are integrals and double integrals are volumes, but then you get into serious trouble talking about triple integrals. So the focus isn't on the 3 dimensions, the focus is actually on what you're adding up over. So the idea here is, so say just for argument's sake we want to find the volume under this surface. Well, we have to add up over this area region, which I'm calling a box. Okay, so this region here, by the way, so this red region, and it's not just the outsides, it's the whole thing. Okay, this region, which I could call a box of some sort, the notation that I would use here is the x goes from -2 to 2, and you do the next bit is the y is going from -2 to 2, so this is actually a square. Okay, and suppose you want to find the volume. Now to find the volume here, what you do is you chop the area into loads of little pieces delta A. So I think we're going to, have we got a picture on the next page? Yeah, so on the next page we're just going to portion this where we're going to chop the thing into loads of little areas. We'll see this on the next page. And then we're going to talk about, say, the volume you're going to add up over the box. Okay, all the little volumes. Okay, so if we define the double integral of a positive function over a rectangle as this is the double integral. Now the double integral, so you can say integrate over a box. You can say the double integral over a box. The double integral notation I'm not mad about, but it essentially boils down to that you're adding up over a two-dimensional region. Okay. So look at the picture on the next page. So this is just kind of a little part of this. Well, not even a part of this. A new problem where you're trying to find a volume. So you see this kind of a curved. Okay, the sides of this are, its 5 sides are perfectly normal story. You know, this is straight, this is straight, this is a face, the bottom is a face, but the top is curved. How could you estimate the volume? Well, what you do is you chop the volume into loads of little pieces. And then you add up those volumes over a rectangle. Okay, so let us take, say this, the volume of this box here. This would be, we're going to call it, I think, the volume of box 1. Okay, now what we're going to say is we're chopping the area we're adding up into loads of little area elements. So this is dA, and you've got two different widths. You've got the side, the width here is dx, and the width here is dy. Okay, and so dA has to be dx by dy. And what we're going to do for each box, we're going to take the centroid, in other words, the midpoint of the box on the bottom. So say, for example, if this box over here is, the volume of this is volume of box 2, here is this midpoint, the middle of this. And what we're going to say is that the volume of that box would be approximated, well, the volume under the curve over the over this is approximated by the volume of the box, which would be, be multiply all the lengths together. So you get dx by dy, and then you're going to take this midpoint here, which I'm calling x2 star, y2 star, and evaluate the function at that point. So that'll be the z value. That will be your height. So the x2 star, y2 star is the middle of this the area here, the second area. Right, we got it. So the volume under this is approximately equal. Just go backwards now. So the volume is defined to be the double integral, which is approximately the volume of the 8 boxes added together. The length of width of the base are dx and dy. We have that. Take this x star, y star is the centroid of each of the rectangular bases. And you take each of the height to be the value of the function at the midpoint, because all of the points on the curve, so if you got a midpoint here, so the top of this is supposed to be on the curve, it's also the height of the box. I'll say the height of the second box is the z value, the z coordinate, and the z coordinate is the value of the function at x2 star, y2 star. Right. So we have that the double integral is approximately, so this is the first one, height by width, well, I don't know, was it height, width, length, is it? So width, length, height. That's the first box. Second box, and there's 8 boxes, so you add them up. Now you have 8, but suppose you have more boxes. And then if you want to make this approximation better and better and better, you take the number of boxes going to infinity, because then you see you've got these things, these boxes are overestimating, underestimating. If you take loads and loads of boxes, so this is the same as taking delta x going to 0 and delta y going to 0, then you get this thing. Okay, this now one thing it says, oh, recall it's difficult to calculate integrals directly from the definition. If you remember a long time ago, you would have calculated derivatives from first principles. You can actually calculate integrals from first principles, but it's just very, very nasty. Instead, what you do is you use the fundamental theorem of calculus, which says that the integral from a to b, what you do if you're integrating a derivative is you anti-differentiate from the derivative to the original function, and then you do top limit minus bottom limit. And you have a similar story here. The fundamental theorem of calculus applies to if you're integrating over an area. Calculating a double integral from first principles is I'd say it's way harder. I don't think anyone has done it, but you can express the double integral as, okay, so we'll see, we'll have to see in an example what the hell I'm talking about there. Oh, we're going to see it on the next page. Right, so suppose you're integrating over a box. So this is where we don't actually talk about the volumes. The important thing is that you think about the region that you're adding up over. And actually, because once we go to triple adding up over a volume, your intuition just disappears. So this is going to be A, B, C, D, and that's this rectangle. And this rectangle, the notation is it's A, B, cross C, D. I might also use the notation box. Okay. So what we want to do here is we want to add up something. Essentially what we want to do is we want to add up the value of the function times delta x, delta y over the whole region. So you got this sum where you're adding up over all the region. Now it's just really like, how do you add up and kind of take essentially for each point you get the contribution to the sum? It's like, what? So what you do is you think as follows. Fix a value of x between a and b. And now I'm going to draw a line, because remember this delta x and this delta y are very, very thin. So essentially we're going to look at this. So we're going to find the contribution to this sum from a single strip. So this has got a width of dx. I don't think that's too important. And the important thing is that it goes from, at this point, y equal to c, up to this point, y equal to d. And what we can do is we can find the contribution to this sum just from this strip. So you got here, so to add up, what you're adding up is f of xi, yi. Now we won't use delta x, and this is kind of what we're dealing with is, instead it's an infinite sum, so it'll be the integral of f of x, y, dx, dy. We're adding this up over the box. So let's just add up over the strip. What you would get is, okay, so along the strip dx is a constant, so that can be taken up, and add up from y equal to c to y equal to d, integrate this thing with respect to y. And this is just a normal integral. And when we do examples, the integrals I asked you to do are not going to be that complicated. And now what you do, to add up over the entire rectangle, you'll add up for all the values of x from a to b, find the contribution to the sum from the strip at x. So if you want to think about it in terms of maybe you've got a density per unit area here, and you want to find the mass of this, essentially what you're going to do is you're going to find the mass of this strip in terms of x, and then add up all the masses from, say, x equal to a up to x equal to b, and all those masses are infinitely small. You're adding up infinitely many of them. You've got an integral. Okay, and so you end up, you can write the double integral, certainly for a rectangle, in this form. with this is called an iterated thing. You can do it the other way around. You can do horizontal first and then vertical if you want, but I like doing it this way always. And most of the time we're integrating over will not be a rectangle. Well, we'll see that when we do examples. Okay, but the basic idea is if you want to add up over an area, add up over a strip first. Okay, so we'll look at the applications of this now before doing examples in the next video. So one of the things is if you're chopping this up, as the mesh gets very fine, the delta A, which is a little bit of area, turns into what you call a fiber, dA. Okay, it's kind of a rough thing. So what have we got here? If rho is the density, is the mass per unit area, aka density, then if you integrate the density against area, that's approximately a sum of density times area, and density per unit area times area is mass. So you're adding up all the little bits of mass, you get the mass. Okay. Now previously we might have used the notation mi equal to delta m. Let us try and explain this a little bit. Okay. So we'll take in general a lamina, which means it's a three-dimensional object, but it's so thin that it can be treated as two-dimensional. We'll take a little, now this one is a little bit difficult to chop up, but we'll do it. We'll imagine that we're chopping it up. So we'll exaggerate this. So this is like actually the first video. So this is dx, dy, and we're going to say this will be a little bit of mass, will it be? Yeah, so in here we're going to have, at this point, we're going to say that the density is rho of x, y. So this will be a point x, y. And so the mass of this little thing here, now this is not to scale at all, because this should be very, very small, is approximately the density times the area, which is dx dy. And if you want to find the mass of the whole thing, you add these up. So therefore, if you add up over the whole lamina, which I should have just called R, but anyway, yeah, okay, this thing this is the same as adding up all the little bits of mass, which I'm going to call delta M. And if you add up all the little bits of mass, you get the total mass. So all these formulas that I'm talking about here, they'll always be given to you in the question. Okay, but just as you go on, if you ever have to have a problem where you have to, like a difficult problem where you have to chop it up into loads of little problems, this is how you end up with an integral, and hopefully you can calculate the integral then using mathematics. Centroid. Okay, will I go through this? Here, we'll give it a... yeah, I think I do it. Okay, so we got a lamina. We'll call it R. And I think how I'm going to do this is as follows. Suppose that this is the centroid. Now the centroid is the bit that it has no internal torques. What that means is you could balance this thing on that point. That's what the centroid is. And so this would be x bar, y bar, and I'm saying that this is the centroid. So take an area element, I think we're going to put it over here now. I'm going to make this one way smaller than last time. So if this is to be the centroid, if I find the torque or the moment of this little mass about this axis and add them all up over the whole lamina, I should get 0. Because all of the things apply a moment, but if it's the centroid, it'll be balanced out. Okay, so this is a little dA here. Okay, it's at the point x. Okay, so whatever force the area element dA acts about x equal to x bar, it'll be proportional to dA. So I'm saying it's a constant times dA. Well, this is just kind of saying, like, imagine this thing just sitting here. This thing wants to rotate. The force we're talking about is gravity, I think, in this one. So it's going down. Um, it's going to be proportional to dA because it's going to depend on the density. If we're assuming uniform density, then what I'm talking about here is like gravity is mg, the force will be mg, and the mass of this is just proportional to the area if the density is uniform. Okay, so what we're going to do is we're going to add up. So let's see, force by distance. Here's force, here's distance, and that is the moment of this about this axis. And if we add all these up over the entire lamina, we have to get 0. Adding them up, and what falls out is a formula for the centroid. Similar story, you get a formula for the y-coordinate of the centroid. The other thing, probably the one that's more important for us in engineering, before we move on to examples, the second moment of area. So suppose we've got some kind of a shape here, which again is going to be a, consider it a lamina. So I think actually, maybe I might be correct in saying this. Well, I'll tell you what I'm definitely correct about. Cross sections are like laminas. So this is like a cross section. So second moment of area of the cross section. Yeah, that's okay. Right. So let's take a little piece of this thing, a little bit of area. It has second moment of area. It's about the x-axis is the distance from here to here squared times the area. So we could say something like Ixx, and say the second moment of area of this, we'll call it say I, little I. So Ixx is equal to, you make this more accurate by so the thing is here, the y squared changes a good bit when dA is big, but if dA is very, very small, it's kind of like a point and there's no real variation in y, and therefore y squared among the little area element. So assume that we're doing that. So then we're adding up y squared by the area, that's y squared, and then the area, dA, but of course we're adding up, especially if dA is small, which means dx and dy is small, we're adding up over the whole lamina, y squared, and dA is dx dy. And so the formula for the second moment of area of a lamina is you integrate y squared dx dy, and this is like a little bit of second moment of area, and then you add them up over the whole region. Okay, we're ready now to look at some examples.